Okay, so welcome everyone. It's a pleasure to have with us this week Mehtaab, Sawhney, and Ashwin, nominally from MIT, but actually speaking to us from New York and Portland. And they will tell us about singularity of discrete random matrices. And as a reminder, this will be the two-part talk with the first part for an overview and then a short break and then more technical details after the break. So please, we can get started.
Thank you so much. So hi, I'm Mehtaab. This is joint work with Ashwin, who will be giving the second half of the talk, and Vishesh Jain. And we'll be discussing the singularity of discrete random matrices. So the motivating question and conjecture in this area, sort of concerning the singularity of discrete random matrices, is consider an n by n random matrix, Mn, with IID Rademacher entries. So by Rademacher here, I mean each entry is plus or minus 1 with probability half. Then the probability, the conjecture is that the probability that Mn is singular is 1 plus little 1 times n minus 1 times 2 to the minus n plus 1. So why this slightly funny expression? The above conjecture can just be restated as saying that the probability that the event that Mn is singular is basically equivalent to asymptotically the event that two rows or two columns of this random matrix are equal up to sign. So to the leading order, this is the only term that contributes to the singularity event. So that this is a well-known open conjecture in the theory of discrete random matrices. And one can generalize this conjecture. So instead of just having Rademacher entries, one can say look at more general discrete random matrices. So for a given random variable psi, let Mn psi be an n by n matrix, which is IID entries psi. We expect that the singularity probability of, we expect that the event that Mn psi is singular to be controlled by the event E sub v, where E sub v denotes, it's controlled by the event that you have a singular, you have a kernel vector that's either 1 and all zeros, or 1 minus, has one coordinate 1, one coordinate minus 1, and the rest are all zeros. So just to restate it, the singularity event is dominated by the fact you either have a kernel vector, which is 1 and all zeros, or a kernel vector, which is 1, minus 1, and then all zeros. You can also have 1 and 1. This might seem a little strange, but you can sort of restate this. If you just write this out, what this is actually saying is that the probability that Mn psi is singular is dominated by the event that either a row or column is all zeros. So suppose this can occur, for example, if your distribution has a large atom at 0, or it's dominated by the event that two rows or columns are equal or equal up to a sign. So the most well-studied case is when the random variable psi is a Rademacher, and the first non-trivial result in this direction is due to Cohn-Loge. It's even non-trivial to show that the singularity probability is a literal 1, and this is a result due to Cohn-Loge, that as you take n to infinity, the probability that this random matrix is non-singular does tend to 1. The first exponential bound was obtained significantly later, almost 30 years later, by Kahn, Cohn-Loge, and Semeretti, who proved that the probability that Mn is singular is upper bounded by 0.999 to the n. So recall from the previous slide that we expect that the singularity probability in the exponent grows at an exponential rate of roughly 1/2 to the n. So this is giving you some exponential rate, but not the sharp exponential. The base of this exponent was then improved in a series of really important works, first by Tao, in first two papers by Tao Wu in 2006 and 2007, who improved the bound to 3/4, and then Bourgain, Wu, and Wood, who improved this exponent to 1/√2. And finally, this culminated in a recent breakthrough of Komarov, who proved that the probability that Mn is singular is 1/2 plus little 1 to the n. So we now know the correct exponential rate for the probability that Mn is singular. In fact, Komarov shows a slightly stronger result, a much stronger result. So instead of looking at Rademacher entries, let's look at Bernoulli P entries. So in particular, your probability, with probability P, you're 1, and with probability 1 minus P, you're 0. Then the singularity, the probability that Mn of Bernoulli P is singular has an exponential rate of 1 minus P plus a little 1 to the n for any fixed P between 0 and a half. However, despite the fact that Komarov was able to obtain the correct base of the exponent, more refined results concerning the sort of the exact asymptotic probability that a random matrix is singular remained open. So in particular, instead of aiming for the correct base of the exponent, we want an estimate. The concern of this talk will be estimates of the form where you have 1 plus little 1 times the 1 plus little 1 times the probability that the matrix is singular. So you want to understand sort of the event more precisely. This is only giving you up to a sub-exponential factor. And due to a flurry of recent work, sort of started by Bosak and Rulson, then Litvak and Komarov, and then Han Huang, we now understand sharp singularity results for Bernoulli P when the probability of being 1 is between log n over n and some small constant c. So let's say 1 over 1,000. And you might ask, why is there this lower bound at log n over n? The reason that there's a lower bound at log n over n is that if you have, if the probability that an entry in your matrix is 0, probability that an entry in your matrix is 1 is less than log n over n, then with high probability, you can show that you have a 0 row or column. So with high probability, your matrix is actually singular. So the problem is not interesting once Pn is much less than log n over n. So given, and in particular, what these results by Bosak and Rulson, Litvak and Komarov, and Huang were showing is that the probability that this matrix with Bernoulli P entries is singular is just controlled by the event that a row or column is all zeros. So in particular, they were showing that the probability that the matrix is singular is 1 plus a little 1 times the probability that there's a 0 row or column. So our main result is an extension of, is a vast generalization of this to prove sharp singularity results for discrete random, for a wide class of discrete random matrices. So to state the theorem precisely, let's recall some events. So the event E sub V denotes the event that the vector V is a left kernel vector, a right kernel vector of your matrix, Mn psi. And we say that a random variable psi is discrete if it's not constant and is supported on finitely many atoms. Then we can prove the following theorem. And this is joint work with Ashwin and Vishesh Jain. So let psi be a discrete random variable, which is not uniform on its support. Then there exists constant c psi, little c psi, there exists a constant little c psi, such that for all n sufficiently large, we have that the probability that Mn is singular is 2n times the probability of the event, the probability that E1 is a left kernel vector, plus n times n minus 1 times the probability that E1 plus E2 is a singular vector, or E1 minus E2 is a singular vector, is a kernel vector. So the result as stated might be a little bit difficult to parse, but let's actually just, one can restate this result as saying that the probability that Mn is singular is controlled by 2 different events. The first event, 2n times the probability that math tau E1, this event is saying the probability that this event is equivalent to the event that either a row or a column of your matrix is all 0. And the second event is the probability that 2 rows of your matrix are the same, or 2 two rows of your matrix are the same up to a sign. So in particular, for discrete random variables, which are not uniform on their support, you have sort of an exact an exact characterization of when they're singular, asymptotically.
Sorry, but if say xi takes values 1, 2, and 3, don't you have a similar term for one row being twice the another row, which would be the same order of magnitude?
No.
Say,
so the problem.
Say 1 and 2 equally likely and 3 less likely, so it's not uniform.
Sure. So there's actually even an issue. So actually, conjecturally, this is always the answer. So let's briefly walk through that example where your entries are 1, 2, and 3 with probability a third each. Then the probability that one, suppose you know the top row, then it's not a probability 1/3 to the n that the next row is twice the first row, right? Because if one of the entries is 3 in the first row, then you can't sort of multiply it by 2 to get an entry in the second row. So you can actually conjecturally sort of, these are the only singular vectors. Does that answer the question?
Yeah. Okay. I see my error.
Yeah. No. I've made this error as well. And we also can prove a result when psi is uniform on support. So when psi is uniform on support of size k, we can prove the correct exponential rate. In particular, the probability that mn is singular is of order 1/k to the n. So this result was stated in quite a bit of generality. Let's specialize the result. So for Bernoulli P singularity, this actually gives the sharp singularity for P not equal to a half. In particular, for P greater than a half, even the base of the exponent is unknown. In particular, Komarov's results only gives you a sharp base for P less than a half, and for P greater than a half, it doesn't. Furthermore, for P less than a half, if you actually just trace through the theorem, you actually get the first two terms of the asymptotic expansion. And in particular, no result of this precision was available before. And more precisely, the singularity probabilities are this. So for P less than a half, it's 2n times 1 minus P to the n. That term is just, that term corresponds to the probability that either a row or column is all 0. Plus n squared minus m times p squared plus 1 minus p squared to the n. This corresponds to the event that 2 rows are equal or 2 columns are equal, and plus a smaller exponential term. And for p greater than a half, it's n squared minus n times p squared plus 1 minus p squared to the n. And notice that this corresponds to the event that 2 rows are equal. So this is in particular why Komarov was not getting a sharp result for P bigger than a half, because the dominant singularity event is not the probability that a row is all 0. Instead, it's the probability that 2 rows or 2 columns are equal. So the broad approach we take in this paper is sort of in the spirit of this geometric approach to random matrix theory. And this approach is similar to that used by Komarov and relies on pioneering work of Rudolphin and Verschanen. So because it's a geometric approach, we're sort of not just going to aim for a singularity probability. Instead, we're going to aim for bounds on the least singular value of your random matrix, which is in some sense a more quantitative version of the original problem. So recall that Sn of m, so like the least singular value of m, is this: you take a vector on the unit sphere and you hit your matrix M against this vector. And you want to understand what is the minimum possible norm of this image. This is the least singular value of M. So an influential result of Rudolphin and Verschanen states that suppose I have an IID Rademacher matrix, then the probability that the least singular value of Mn is less than T over root n is less than C times T plus 2 times e to the minus Cn for some constants big C and little c. Furthermore, this result is significantly more general than I've stated here. It doesn't hold for just Rademacher matrices, IID Rademacher matrices. It holds for any random variable psi, which is sub-Gaussian. And big C and little c then depend on the sub-Gaussian moment of your random variable. And the broad approach taken by Rulson and Verschanen is to understand this least singular value by decomposing the sphere into two parts. So in particular, we're looking at the minimum value of m times x for x over the sphere. So what we do is we divide the sphere into two parts. The first is where x is a compressible vector. So in particular, you should think of x being very, an example of compressible vectors are very sparse vectors. So in particular, a unit vector that's of the form 1 and then a bunch of zeros would be compressible. And then the other part of the sphere is the incompressible vectors. So let's say where all the coordinates are of size 1 over square root n. And the key point is that for the compressible vectors are a very small portion of the sphere. So one can use a direct argument to handle this. While for incompressible vectors, what Rulson and Verschanen do is they reduce this, understanding this least singular value estimate to understanding the probability, understanding the distance of the final row of the matrix from the remaining rows. So let's step back. So the compressible case, you're just sort of going to handle it by hand. And for the incompressible case, you're going to instead try to understand, instead of sort of understanding the least singular value directly, you're going to try to understand the distance from the last row to the remaining rows. And this makes some sense because if the last row of your random matrix is in the span of the first and -1 rows, then you know that it's singular. And the event that the least singular value is equal to 0 is the same as the event that the random matrix is singular. And in some sense, as we go through the talk, I'll give a more quantitative version of this, which is key for this approach. So let's give some brief intuition for this strategy regarding splitting the sphere into compressible and incompressible parts. So as we saw earlier, the singularity of a random IID matrix is controlled by the probability it has like a sparse left or right kernel vector. So in particular, we had discussed that the probability that the random matrix is singular is controlled by the probability that 2 rows are the same or there's a 0 row or 0 column. This corresponds to having a left or right kernel vector that is supported on only 1 or 2 coordinates. So this is a very atypical vector on the n-dimensional sphere. And given this, all work on the singularity problem, even going back to Komlosh, use proxies for sparse versus non-sparse vectors on the sphere. However, in the geometric method, we're sort of aiming for some sort of a singular value estimate. So one needs a more robust notion of this sparse versus non-sparse distinction. In particular, if you have a vector which is, let's say, 1 minus 1 over square root n on the first coordinate and then is evenly distributed on the rest, this in theory is non-sparse, but somehow it looks like a sparse vector. And when we're sort of looking at singular value estimates, you need to treat this as a compressible vector. And that's why we'll need some more robust notion than sparse versus non-sparse. And the key intuition here is, or one of the key intuitions is that since the compressible vectors are sort of a very small portion of the sphere, in particular, a random vector on the sphere is not going to have a very small subset of coordinates, which have a large portion of the L2 mass. You're going to be able to handle these directly. And for the remaining parts of the sphere, you're going to have to do something slightly more intricate. So the key idea behind the Rulson and Verschanen analysis of compressible vectors is the following fact. So let X be any fixed vector on the sphere. So for simplicity, I'm just gonna, for a lot of the motivation, I'm going to only focus on the case where this random variable psi is Bernoulli P. And for most of the talk, it's fine to keep in mind. It's fine to keep in mind sort of the case where you're probably 0 with a half and probably 1 with a half. Towards the end of the talk, I'll end of this section, I'll explain where the p less than a half comes in. So what they prove is that for any fixed vector x on the sphere, the probability that mn, so your random matrix times x, is smaller than c root n is exponentially small. So in particular, outside of an exponentially small probability, for any fixed vector x, you're of order root n. The image of that vector is order root n. Furthermore, sort of since Rademacher Rademakers are sub-Gaussian, you can show by sort of very standard sub-Gaussian concentration that there exists some constant k such that the operator norm of this random matrix being bigger than some large constant k times root n is less than 4 to the minus n. So now we take a net over the compressible vectors. So let me define compressible formally. So we say a vector is delta rho compressible if it's rho close to some delta n sparse vector. So in particular, what we mean by compressible is that you have most of your L2 mass on some like very small chunk, like some small but linear sized chunk of the vector. And we say a vector is incompressible if it's not compressible, if it's on the remainder of the sphere. And the key point is that you can take an epsilon net of the compressible sphere is much of the compressible subset of the sphere is much smaller than an epsilon net for the whole sphere. So in particular, if you're keeping track of constants, we're going to choose epsilon to be this little c over 2 times k. It's not so important, but the key point is if you choose the parameters in the correct order, using this fact that for any fixed vector, the probability that your image is very small is exponentially small, we can show is that the probability that some compressible vector has image less than c times square root n over 2. Suppose some compressible vector has image less than c times square root n over 2. Then by rounding, and under the event that your operator norm is small, you can show that it suffices to just look at an epsilon net of the compressible vectors. So a priori, the compressible vectors are an infinite collection of vectors, so I can't take a union bound, but you can just take an epsilon net and you can show that the event that some compressible vector has small image can be turned into the corresponding event on the net at the cost of some constants. And basically, if you choose sort of the compressibility parameter small enough, in particular, you say you're, let's say, very close to a vector which is n over 1,000 sparse, let's say, then you're able to show that this union bound goes through. So in particular, with exponentially small probability, you have that over the, with all but exponentially small probability, you have that you're large over the compressible part of the sphere. And you could, it's sort of what, notice that nothing I said actually requires that I look at compressible vectors. It's just that I can deal with any low metric entropy part of the sphere. What I mean by low metric entropy here is that you have a small epsilon net. You just need your epsilon net to be small enough that the union bound goes through. However, note that we're aiming for something very precise. We're aiming for a probability of 1 minus p to the n. And this e to the minus cn is not high enough, not a good enough quality in order to achieve that bound. So the key proposition for Komarov's improvement is the following elementary inequality. So first, we'll need to briefly recall what the Levy concentration function is. So the Levy concentration function of a random variable x is the maximum probability that x lies in some interval of length 2 times epsilon. So it's sort of telling you how concentrated your random variable is. And the key idea for Komarov is the following lemma. So fix p between 0 and 1/2. Then there exists some delta, which is a function, some theta, which is a function of p, such that for any vector x on the sphere, if I look at the inner product of x with a set of Bernoulli random vector against a Bernoulli random vector, then the Levy concentration of that sum at a scale theta is less than 1 minus p. So somehow notice that you can't do better than this 1 minus p, because one such unit vector is 1 and then all zeros. And then this is saying that the Levy concentration of B1, I can choose some theta so that the Levy concentration of Bernoulli is some parameter theta, so that's less than 1 minus p. So, and notice that this fact is somehow much more precise and sort of looks at the Bernoulli much more carefully than anything we've discussed with with the work of Rulison and Verschen. And this inequality is actually quite easy to prove. It's completely elementary. So there are two cases. First, there's the case where you look at this vector x on the sphere. If this vector x on the sphere has a very small L infinity norm, then the sum bi xi is going to converge to some Gaussian. So just, you can sort of prove this Levy concentration fact for free because your distribution is sufficiently close to some Gaussian, and this just falls out for free. Otherwise, you can order the coordinates, and without loss of generality, let's assume that x1 is the largest coordinate. Then you know you have a lower bound on the largest coordinate of something like delta p. Furthermore, the Levy concentration function goes down when you add independent random variables. So in particular, the Levy concentration of b1 x1 plus b2 x2 plus dot dot dot. Notice that the part of b2 x2 plus b3 x3 dot 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 is independent of b1 x1. So it's sort of easy to see just by convexity that the Levy concentration of this whole sum at a scale theta is upper bounded by the Levy concentration of b1 x1 at the scale theta. But now this is basically just understanding the Levy concentration of a Bernoulli random variable. And since we have a lower bound on x1, we know that the 2 points of this distribution, which are at 0 and x1, are separated. So I can pick an appropriate theta, which is sort of is whatever the lower bound on x1 is divided by 4, and you can get a bound. So this is telling you, so let's step back for a second. What is this saying? This is saying that I look at, this can be restated as saying the following. Suppose I have a random matrix where every entry is Bernoulli p. Then I take a row of this matrix and I take the inner product with your vector. The probability that this inner product is in some interval of length 2 theta is upper bounded by 1 minus p. So then, sort of just by applying Chernoff naively, what you get is that for any vector x on the sphere, the probability that mn times x is less than some constant in terms of p and epsilon times root n is upper bounded by 1 minus p plus epsilon. And then choosing you can take epsilon arbitrarily small, adjusting constant cp epsilon. And then you can sort of round to a net of compressible vectors as before, and you get the desired result on the set of compressible vectors. However, so at this point, we now understand how to get sort of a bound of the quality 1 minus p plus epsilon to the n for the set of compressible vectors. Ashwin, in the second half, we'll show how you can refine this to sort of get 1 minus p to the n plus some lower order terms, which is actually important for our result. But we still haven't dealt with the majority of the sphere. We've only dealt with the part of the sphere that's compressible. So sort of the set of vectors which have a lot of mass concentrated on a few entries. This is sort of like a very atypical vector on the sphere. This is, in fact, you're still missing most of the sphere. And sort of the key idea for this part is a reduction to hyperplane distance estimate. So, so there's this lemma by Rulison and Verschen that allows you to reduce understanding the minimum of your random matrix A times some incompressible vector to understanding distances to hyperplanes. So let me just briefly go through it. What it says is that so on the left you have this probability of having an incompressible vector, which has small image. This is upper bounded by the probability that, that you have some row k whose distance to the span of the remaining rows. So, okay, let me step back. Let Ri be the ith row vector, and Hk denote the span of the remaining rows. Then the probability that you have a small vector which is incompressible is upper bounded by the probability that the distance from this row to the remaining to the span of the remaining rows is small. And this sort of is turning a probability which is somehow difficult to handle. You're taking you have to take a union bound over all incompressible vectors into something that's much more manageable. Because if you understand, let's say if you understand sort of the normal vector to this hyperplane HK, then you can sort of understand this distance of RK to HK is just some inner product that you need to handle. So in particular, as I stated, the distance from RK to HK is just the inner product of the row RK with HK star, which is the unit normal to HK. This is just some linear algebra. And therefore, the key issue at this juncture is to sort of understand what's called the additive structure of the normal vector H sub k, the additive structure of this unit normal HK star. And furthermore, you can sort of, if you sort of do this reduction very carefully, you can sort of check that this unit normal we have is always incompressible. So in particular, you're never going to have a unit, we're never going to have to deal with a unit normal, which is sort of sparse. So you have a guarantee that you have sort of many non-zero coordinates. So at this point, the singularity probability is basically down to understanding the inner product of this row with the unit normal to the remaining rows. So and understanding the probability that this event is small, the probability that this inner product is less than t. And notice that if you're only looking at the singularity probability, then sort of you only care about the case where this inner product is exactly 0. Now, suppose for a second that R sub k was not a set of Bernoulli p's, but instead was a set of Gaussian random vectors. Then RK, the inner product of RK and HK prime would actually be just a Gaussian of unit variance. So then this probability that you're less than t is something like order t. But this breaks down at t equals 0, because you can have a positive probability of being 0, because RK is not sort of some absolutely continuous distribution. Instead, it's just it's a random vector on the Boolean hypercube. So in particular, it has atoms. And by our analysis, we already know that HK is not compressible with high probability. And what you can, if you know this fact, then sort of what does a classic inequality of Erdős-Littlewood, the classic inequality of Erdős-Littlewood and Alford implies that if HK has support size at least delta times n, then the probability that this inner product is 0 is at most some constant times 1 over the square root of the support size. So in particular, if you actually use this inequality plus our earlier handling of compressible vectors, you can actually just reprove Kolmog's result. And that's actually very close to how we did it originally. However, there's an issue here, because the Erdős-Littlewood-Alford inequality can be sharp. So in particular, to understand how it can be sharp, just imagine that the unit normal is a scaled multiple of the all ones vector, and the rows are Rademachers. So then this is a sum of n Rademachers, and the probability that the sum of n Rademachers equals 0 is approximately 1 over square root n. And therefore, this shows that in general, you can't do better than 1 over square root n by just assuming that you're incompressible. So you actually need to do something more. And So in particular, we now need to understand these small ball probabilities. So probability that RK times this unit normal is less than P. And suppose for the rest of, for now that this, these RKs are distributed like Rademachers or Bernoulli P's. So the issue we had earlier is that if HK was all, was sort of a scaled multiple of the all ones vector, then sort of many of these events were coinciding. So you're getting a very large probability of being zero. And you can actually you can sort of scale this. So in particular, if your unit normal can be scaled by some parameter theta, and then it looks like an integer vector, then you can show that sort of you get a small ball probability of order t plus 1 over theta. And similarly, you don't exactly need that theta times your unit normal is exactly an integer point. Instead, what you need is that there's some small multiple theta times your unit vector times your unit normal, which is close to an integer point. And the key idea of the work of Rudolph and Shannon is to sort of formalize this in some way. In particular, they introduce a notion of arithmetic structure called the essential least common denominator. So in particular, what the LCD tells you is that what is a reasonable theta. So in particular, the LCD is sort of capturing this notion. What is the constant that you have to multiply your unit normal by? So that's approximately an integer point. And in particular, if your LCD is order if you have an LCD of order theta, then you sort of can control small ball probabilities, which are of size 1 over the LCD. And this is done by Esse's inequality. And then sort of if you're aiming for just an exponential singularity result, the key goal is to show that the LCD of your unit normal is the probability that this unit normal has LCD less than exponential size occurs with exponentially small probability. And this can be done. And sort of this is essentially the roadmap for Rudolph and Shannon. However, this is sort of not looking at the concentration function directly. Instead, you're trying to understand this geometric structure of this unit normal. And it turns out, therefore, that the LCD becomes a little bit too imprecise to prove these sharp singularity results. And so one of the key issues that Tikhomarov has to overcome is instead of having this nice geometric quantity, he sort of has to directly deal with the small ball probabilities. So in particular, he has to understand when is this probability small? So instead of looking at some proxy like the LCD, which then controls a small ball probability, Tikhomarov is able to deal with the small ball probability directly. And in particular, what he shows is that sort of for all but a super exponentially sparse subset of potential kernel vectors, that you get the desired control on the Levy concentration function. So in particular, you can control the Levy concentration function all the way down to scales of 1 minus p plus epsilon to the n for Bernoulli P's. And notice that you really can't hope to do any better than this, because when you look at your row R sub k, there's an atom of size 1 minus p to the n. So you can't hope to control sort of probabilities which are much smaller than that, because you actually have an atom of that size. So in general, one cannot show a probability better than 1 minus p to the n. And sort of because you'll eventually have to eventually take union bounds, and sort of this sort of turns out you can never get better than, you sort of can never get a result better than 1 minus p plus epsilon to the n for some for some not so slowly growing function epsilon of n. And so we need to do, in order to prove a sharp singularity result, you actually need to do better than this. Notice, however, that this event that's giving you a Levy concentration function of 1 minus p to the n comes from an atypical event. In particular, it comes from the event that that you have an all zeros row. Sorry, it's written all ones row. It should be an all zeros row. And this is pretty atypical. And indeed, sort of if you just do naive turnoff, you can sort of look at the rows of your random matrix. And in particular, with all but a very small exponential, almost all your rows have approximately p times n entries. And the key idea of Litvak and Tikhomarov is to sort of exploit a sort of gap between a typical row and this very atypical event that's giving you this this barrier at 1 minus p to the n. So in particular, there's an exponential gap between 1 minus p to the n and sort of the entropy of a slice that has pn ones. So the entropy of the slice, which is pn ones, and the number of choices when you have pn ones and 1 minus p times n zeros is n choose pn. And it turns out that 1 minus p to the n is bigger than 1 over n choose pn. And there's this exponential gap in between this. And therefore, one could hope to prove that if you have you could hope that if, let's say, your random row has exactly pn's and 1 minus pn ones and 1 minus p times n zeros, then the anti-concentration of your row times your kernel vector grows like something like 1 over n choose pn. And roughly the key idea here, the key idea of our work is to prove a sufficiently good, prove an analog of the result of Tikhomarov showing a super exponentially sparse subset of the kernel vectors sort of satisfy this property. And this is good enough to prove the higher quality estimates for the sharp singular. This is good enough to prove the higher quality estimates that we've mentioned. And this also explains why we're not able to deal with p equals a half. In particular, we don't have this exponential gap between 1 minus p to the n and choose pn. And that's why we no longer are able to prove a sharp singularity result when the p is equal to a half. So that's all I had intended to speak about during the broad overview. The papers, if you're interested, are available on the archive with the same title as the talk. Thank you for your attention and any questions for the first half of the talk.
Thank you. Yes. So indeed, we will take a short break now before continuing, but anyone can stretch and such. But if there are any questions, now would be a good time. And I guess one question that comes up. So you said that you get the first and second terms in some expansion for the probability of singularity, but is there some expectation for what some additional terms might be? So you have the dominant terms from one row and or two rows or columns.
Yeah. So it's sort of the conjecture is basically it comes from sort of very sparse events. So in particular, I think the next order, if you look at Bernoulli a half, is the probability that 4 rows sum to all zeros. So in particular, the probability that 4 Bernoullis sums to 0 is 3 over 8. So the probability that that 4 particular rows sum to 0 is like 3/8 to the n. And sort of the guess for this expansion is just sort of enumerate over very short vectors like this, and that's what it should be.
There's a paper by Orazio and DeSalvo, I think, or something of that sort, where they basically discuss what this expansion should look like for Rademacher. But it's already quite complicated because you have to like subtract off the intersection events and other issues. So it's some sort of, you can think of it as analogous to some sort of cluster expansion from statistical physics. Like you can sort of predict every term if you really, really care. But the actual exact numbers, it becomes like very combinatorial as well, I think. Yeah. But the first 2 terms are usually pretty easy to figure out.
Okay. I see. So the expectation would be that for any discrete distribution, you would have a similar combinatorial expansion, and Rademacher maybe has the richest structure of potential.
Basically.
Yeah. Exactly. One, I guess, case that would be particularly simple is imagine that you had a random variable that was only supported on like some sort of transcendental numbers. Then it's actually much easier to figure out what the event should be coming from, because then the only sort of like events that can happen, the only dependencies are going to come from having things like 2 equal rows or 3 equal rows, stuff like that. And it's and that I think is a good model to think about. But of course, these plus minus 1 models are the ones that are most studied. Mehtaab, can you stop sharing so I can start sharing the slides from my screen?
Jonathan, you here?
Does this look fine?
Yes.
Okay. Yeah, so thanks for staying. Okay, so I guess I'll briefly go into sort of dive deeper into a couple of aspects of these arguments that Mehtaab had briefly outlined. So just to sort of recap what had happened in part 1, in order to understand when a random matrix is singular, we sort of decompose the possible kernel vectors into 2 types. Compressible, which corresponds to sparse vectors, and incompressible. And with the compressibles, we saw that there is a way, using the analysis of Rudolphin-Verschuinen, as well as of T. Komarov, to essentially almost sharply, up to a sub-exponential factor, analyze their contribution to the singularity probability. Then, in the cases where you have an incompressible kernel vector, we reduced the singularity event to the event that some row is close to the span of the remaining rows. Equivalently, the dot product of a row against the kernel vector, the dot product of a row against a unit normal to the remaining rows. And then we understood the structure of that unit normal and showed, in some sense, it did not have, or was very arithmetically unstructured. And from there, we were able to proceed. So I'm going to sort of dive into 2 aspects of the argument, one from the compressible side and one from the incompressible side, and see where some of these sharp results are really coming from. Okay, so I'll start with compressibles. So first, let's just, sorry. Okay, does this look, okay, sorry. Okay, so first, let's think about the compressible vectors. So recall these are vectors which are very sparse. And the analysis of Rudolphin-Verschuinen just used
screen?
I wasn't able to move back and forth. Yeah,
okay.
I hope this is fine.
That's fine then.
Yeah, okay. So Rudolphin and Verschuinen just used the fact that you had a very sparse vector to get some sort of probability event, because there aren't many of those vectors. T. Komarov showed that any fixed vector actually cannot sort of do better than the vector 1 and a bunch of zeros. And by doing this in a quantitative manner, he was able to show a sharper result, namely 1 minus p plus epsilon to the n. So how do we get the sharp answer? We need to be able to isolate very precisely the vectors that are 1 and a bunch of zeros, for example. So the elementary vectors, E1, E2 up to En. And so to that end, let's let the elementary vectors be those which are delta close to one of these elementary vectors, E1 up to En. And the starting point for this analysis that we're going to provide, which is more sharp, is the following lemma. So basically what this is saying is that as long as I take a vector on the sphere that is not delta close to an elementary vector, then its dot product with a row of my random matrix is not only 1 minus p anti-concentrated, but is even less than 1 minus p. So recall that Tikhomarov showed that for any vector on the sphere, this dot product had a concentration of 1 minus p. And here we're saying, okay, as long as you're not near the vector which I secretly know is the correct kernel vector, you can actually do a little better. And that slight epsilon of room is enough to get to be able to rule out a large class of vectors without being very lossy. Okay. As you can see, this is very similar in flavor to Tikhomarov's lemma. So I'll just outline roughly how this is proved. So Tikhomarov put into cases whether the largest element in the largest coordinate of x is big or small. And so we're going to do something slightly more refined. So first of all, if the large coordinate of x is very small, again, we know that b dot x looks approximately like a Gaussian. And so again, a quantitative central limit theorem is going to suffice. If we have two large coordinates, then similar to this Tikhomarov argument, we forget about the remaining coordinates and we just focus on b1 x1 plus b2 x2. And since both x1 and x2 are large, you can show that the four possible values that this random variable takes on are separated from each other in an appropriate sense, so that the worst possible point mass that you could get out of this random variable is p squared plus 1 minus p squared. And again, you can get the result, because this, when p is less than a half, is strictly less than 1 minus p. Finally, in the case where you have exactly one large coordinate, because we are not super close to the vector E1, for example, we know that that large coordinate is upper bounded by 1 minus delta, or 1 minus delta prime. And therefore, the remaining coordinates are going to have a large L2 mass, but all of those coordinates are small. And so again, we can apply a quantitative central limit theorem just on those remaining coordinates and get it to work. So the point is, as long as we are not near this one special, or these n special vectors, E1 up to En, we're going to get something that is just a bit better. And okay, using a similar sort of Chernoff argument, as well as a net argument, we can rule out all of the compressible vectors with very good probability, 1 minus p minus epsilon to the n, which is smaller than 1 minus p to the n. We can rule out all of those vectors except for the vectors which are delta close to E1, E2 up to En. Okay. Now, when we're close to E1, for example, we're going to need to do something more refined. Because of course, in the case where E1 is actually the kernel vector, that is going to be exactly 1 minus p to the n. And we need to show that for the vectors that are very close to E1, we can extract precisely the correct probability out. And more generally, for general discrete distributions, and also for the case p greater than 1/2, a similar analysis will reduce to being close to E1 or E1 minus E2 or E1 plus E2, which are sort of the main events in general that one needs to consider. But I'll focus on this case as it is the most salient. Okay, so we have a kernel vector which is very close to E1. What do we do? So for simplicity, I'll just write my random matrix, which is Bernoulli P, as Bn of P. And suppose we have a vector which is delta close to an elementary vector. And by symmetry and by scaling it up very slightly, let's just assume that the first coordinate of this vector equals 1, and the remaining coordinates are small in length, in L2 length. Okay. What we do is we basically try to figure out what the product of this vector with the random matrix looks like. So let's decompose the random matrix into B11, which is the top left coordinate, the row next to it, which we'll call R, the column under it, which we'll call S, and a remaining n-1 by n-1 block. Now, if we multiply U on the right by BNP and we set it equal to 0, let's say, we can solve for U prime in some sense. And we deduce that the first column of this random matrix, which is here, is equal to negative of the remaining block times U prime. And note that this block is an n by n-1 matrix, which is random, and U prime is a n-1 dimensional vector, which is small. Okay. From this, I claim we can actually understand a lot about the structure of what the random matrix must be in order to have this kernel vector. In particular, a similar fact to the concentration of norm that Mehtaab had described earlier is that BNP is very close in operator norm to its the expected value of the matrix. So the expected value of the matrix BNP is P in every single coordinate. And that's the dominant behavior of that matrix. And if I subtract that out, I'm going to get something which with a very, very high probability, very, very exponentially high probability, has a k root n size operator by standard sub-Gaussian estimate again. Now, since we have that, and since U prime is very small, then it turns out that when we multiply U prime by this block, we can show that that value is at most, say, delta k root n away from P11 transpose times U prime. But P11 transpose times U prime, or if you shift it appropriately so the dimensions match up, is actually an all constant vector. And so what that means is that in this case, in order to have U prime be a kernel vector, this right-hand side has to be very close to an all constant vector. That is to say, this left-hand side, which is just the first column of our random matrix, has to be very close to an all constant vector. Yet, this vector is on the cube, and it's more likely to be all zeros than it is to be all ones. And so we can show that the total probability of the first column being very close to a constant vector is 1 minus p plus little o 1 to the n, just immediately. So this is quite good, but this is not enough to get bounds of the correct form, because as I mentioned, we want to beat this and we want to get the exact probability out. So we need to do just a little better. Okay, so how can we do that? So we use the fact that U prime is small to show that the first column is in some very small probability size. However, we have not used any of the remaining randomness in this random matrix. So the one fact that we have not used is that, okay, first of all, if the first column is 0, we're happy because that is the desired singular event. But if the first column is not 0, we know that it is in the image of this n by n minus 1 block matrix. So just from this equation, this first column is in the image of this n by n minus 1 block matrix, which is random and independent. And suppose we have a non-zero vector, which is in the image of an n by n minus 1 random matrix. It turns out that the seminal work of Rudolphin and Refinements not only applies to singularity random matrices, but you can also use it to bound things like, suppose I have a fixed vector, what is the probability that it lies in the image of a n by n minus 1 vector, or n by n minus 1 matrix, for example. And it turns out that for any fixed column that is non-zero, it will, with exponentially small probability, not be in this image. And that gives you an extra exponential as long as the first column is non-zero. And that's enough to complete the argument. So to summarize, for this refined compressible analysis, we first localized to near an allometric vector. Then using that, for example, if that vector was E1, we showed that the first column is almost all zeros. That's not quite enough to finish. So we also then notice that if that column is non-zero, it must lie in the image of a random matrix, which occurs with exponentially small probability. And those two facts combined push us past the barrier. Okay. More complicated, but in spirit, similar arguments are used for the more general case. So now let's move on to the incompressible vectors. So Mehtaab had introduced this problem of arithmetic structure for the incompressible vectors. Namely, we wanted to understand what the kernel of n-1 rows, or the unit normal to one of these hyperplanes, random hyperplanes, what it looks like. And we wanted to show that the unit normals give us good small ball probabilities. And what we had said is that it's plausible that by changing from an independent model to conditioning on a certain slice, conditioning on the sum being some fixed number, you might be able to exploit the exponential gap which is introduced. However, there are difficulties. So working on the slice has always been difficult. And one example of that is if you look at the following random matrix model, where I take n independent random rows, and each row is uniform on the Boolean cube with sum exactly n over 2. So each row is independent from each other row, but the coordinates in that row are not independent from each other. They're conditioned to have sum n over 2. This should have exponentially small singularity probability, just like the other models. But in fact, an exponential singularity probability was only shown a couple months ago by Tran using a combinatorial LCD. And Litvak and Tikhomarov, also some months ago, used a variant of the LCD, which is called, which they called the U-degree LCD, which they were able to use to apply to slice random variables and their anti-concentration properties. However, it is still lossy. And for that reason, this is one of the key reasons why they can handle sharp singularity estimates for Bernoulli P random matrices when P is less than some very small absolute constant, where they cannot go all the way up to near 1/2 because of that law. As Mehtaab had mentioned, our arithmetic structure results, which is one of the key innovations in our work, develops an analog of Tikhomarov's sharp Bernoulli singularity results, but for the slice. So let me talk first about, at a high level about what Tikhomarov shows and sort of show how we modify and generalize that result. Okay. So the heart of Tikhomarov's paper on Bernoulli singularity, after simplifying numerous technicalities, is the following sort of technical anti-concentration statement. At some level, as Mehtaab had mentioned, we want to show that there aren't many potential kernel vectors that are very structured. As he said, when you apply Irish-Littlewood offered, you get this probability of 1 over root n. But in general, you want a small ball probability which goes all the way down to 1 over 2 to the n. And in some sense, Tikhomarov is going to count potential kernel vectors that don't do as good as 2 to the negative n. And he's going to show that there aren't many compared to what you'd naively expect from just counting vectors. Although there are numerous reductions that are involved in this process. But at the heart, this is the following sort of, this is a simplified case of his key technical results. So let's look at Bernoulli P. You can assume that P is 1/2, although I'll say P is less than 1/2. And let's choose some very small epsilon. Then there's L such that this statement holds. So what I do is I consider some scale, capital N, between 1 and 1 minus P to the negative n. So when P is 1/2, N could go all the way up to almost 2 to the n. And then what I do is I look at vectors where all the coordinates are between n and 2n. and I take its dot product with a row of my random matrix. And I look at the probability that this random variable is within some root n interval. Okay. Suppose that there is some root n interval where I have a high probability, namely L over n. I claim that there aren't many such vectors. So the total number of possible vectors x that I'm considering here is around n, capital N to the little n. And the statement is saying that there is a super exponential fraction of these vectors that satisfy this condition at the most. So just to clarify what this condition is really doing, so notice that B is an independent Bernoulli vector, and X has length around capital N times the square root of little n. So you can check that the variance is order capital N root little n. And we're looking at an interval of size root n. So really, this is controlling the small ball probability at a scale which is 1 over n times the standard deviation. So if you then imagine scaling this vector x down to the unit sphere, we're really controlling small ball probabilities at the scale of 1 over n. And in some sense, we're counting the vectors which fail to have a good small ball probability, so which have a small ball probability which is bigger than 1 over n in size at that scale, when n is not quite 2 to the n. And the point is, since there are a few of these vectors, structured vectors at every possible scale of anti-concentration, we can derive some sort of necessary sharp result. So I will not go into the details of that. And really the key is this super exponential fraction that T homomorph gets. It's e to the negative omega of n. Because at some point you're going to run a union bound over the potential kernel vectors that could show up. And it turns out that you need a super exponential fraction to get a small enough net of your potential kernel vectors that everything will work out. Okay. So this is sort of the key statement that is proven in T. Komarov's results. For us, we need a generalization and extension to the slice. So again, I'll focus on sort of the simplest case of this. So let's fix some p, I'll say between 0 and 1, although you can think of p as being less than a half again. And let's choose some very small epsilon. Then we have the same sort of statement. But instead, capital N is allowed to be as large as n choose Pn, approximately. And again, we're counting vectors in a box, although it's for technical reasons, it's a slightly different box. And the key difference is that the distribution of this random variable here is not independent Bernoulli p's, but instead is on the slice of size p times n. And so, as you can see, every possible value, every possible vector b occurs with probability 1 over n choose Pn. And as Mehtaab mentioned earlier, the fact that 1 minus p to the negative n is much less than n choose Pn when p is less than a half, it provides the key exponential gap for us to be able to remove these little ones in the various parts of the argument. So I won't get into too much detail about how that part is done, but you can sort of compare this result, which is on the slice and sort of goes up to the correct level on the slice, to T. Komarov's result, which goes up to the correct level for an independent random variable. Okay. So let me just say a couple words about how T. Komarov proves his result, and then how we extend. So just recall, we have a statement here. So T. Komarov wants to control the event that x is such that the Levy concentration of a Bernoulli rho dot x is super large. And he wants to show that it's not very often bigger than L over N for some constant L. So first, what T. Komarov does is a combinatorial counting argument in order to show that if I reveal the first 1 minus epsilon or 1 minus epsilon tilde coordinates, fraction of coordinates of my vector in my box X, then already with super exponential probability, I will, super exponentially small probability will this event occur that is bigger than L prime over N. The problem is that L prime is going to grow depending on the super exponential probability that I want to maintain. So as omega n goes to infinity, L prime will also be growing. So in order to get the result that we need to decouple L prime from L, or decouple L prime from the omega n. Luckily, we still have epsilon tilde n remaining coordinates to do so. At this point, Komarov will reveal the remaining epsilon tilde fraction of coordinates in chunks. And for each, when he reveals each chunk, he'll use it to show that in some sense, the Levy concentration function smooths out even further as I reveal more and more coordinates of X, in a way such that I can actually quantitatively decrement L prime by a factor of, say, 0.75 or something. And I do this for many steps until eventually L prime hits L. The actual argument that allows you to reduce the value of L prime while maintaining a good probability estimate when revealing these chunks is a form of L to L infinity decrement, which I won't get into here. At some level, though, you can imagine that if I reveal the first k coordinates of X, and I just look at v dot x from those coordinates, then I get some distribution on the real line. Then as I reveal more and more coordinates of X and start taking larger and larger random sums, I'm going to sort of take shifts of this distribution and average them together. And this will sort of smooth out the distribution. And this L to L infinity decrement argument has to do with showing that the number of spikes in some sense will quantitatively reduce over time. Our proof for the slice, sort of just to describe our generalization, involves a more complicated initial combinatorial counting estimate in order to extract this entropy behavior of n choose Pn on the slice, first of all. Then we will still have to perform an analogous decrementing strategy as with T. Komarov. This time, because we don't have independent, because the coordinates of B are not actually independent, doing this is slightly complicated. And so at some level, morally, we use resampling on the slice in order to produce enough independent randomness that this smoothing effect will still carry through. Okay. So now let me just say a couple words about what happens in general. So for more general discrete distribution, rather than just Bernoulli P, one of the key points is suppose that I have my discrete distribution psi, which is supported on points A1 up to AK. Then instead of just working on a slice, in some sense you have to work on very general multi-slices, where I look at a random vector, a random row of my random matrix, and I condition on it having mj indices equal to aj for every atom aj, where the sum of all of the m's is equal to n. As I had already mentioned, for the compressible estimates in this very general case, the arguments also become substantially more involved just because not only do we have to handle vectors that are near E1, we need to handle vectors that are near E1 minus E2. And for that, for example, you're going to have to somehow reveal the first two columns in some way, reveal stuff about it, bound their behavior, and also run this other argument this more refined argument and put it all together in a way without sacrificing too much, among other issues, which I won't get into here. Okay. So that's all I have for part 2. Again, both the papers are available on the archive with the same title of the talk. Thanks for your attention, staying. Are there any questions about sort of the second part?
Okay, yeah, thank you. So I will mute everyone to thank both speakers. And indeed, if there are any further questions at this time, I will stop the recording in any case.